Hey everyone, welcome back to Real Analysis 1. This will be part B of lecture 10. So where we left off was we defined what is meant by an open set and a closed set, and we cranked out a couple of good theorems, including one where we talked about the union and intersection of finite and infinitely many open and closed sets. And so we just finished with that and some good examples. We want to keep moving. And so we've got another theorem here that kind of ties this idea back to a previous concept. But the theorem says that a subset F of real numbers is closed. It's closed if and only if F contains all of its limit points. Okay, the limit points. Do we remember what limit points are? We remember we said that a limit point P of a set E is such that for all epsilon greater than 0, for all epsilon greater than 0, the set, the epsilon neighborhood of P minus P itself and E is non-empty. Right. The basic idea is that a point P is a limit point of E if, for no matter how close you get to P, you always have some element of E that isn't P inside your epsilon neighborhood. Okay. So another way to say this is that the epsilon neighborhood of P contains a point from E that is not P for all epsilon greater than 0. Right. So it's always possible to shrink your epsilon neighborhood down and still have an element of E inside that neighborhood. And that's a limit point. Okay. So what this is saying is that a subset F is closed if and only if it contains all of its limit points. Okay. And hopefully you can kind of start to see how interior points and limit points and all of these concepts are connected and related. All right, let's go ahead and prove this one. This is an if and only if, so it's two directions. So we'll start with the direction where we assume that F is closed. All right, so assume that F is closed. So F is closed. So that implies then that the complement of F is open. And what's the implication there? Well, for all P, the implication there is that for all P in the complement of F, in F complement, there exists an epsilon greater than 0 such that the epsilon neighborhood of P the epsilon neighborhood of P is in F complement, right? So it's an interior point. P would be an interior point, right? If F complement is open, then every element in F complement must be an interior point. So you have this. Okay. So every epsilon neighborhood of P is, well, not everyone, but there exists an epsilon neighborhood of P inside of F complement. Okay. And so what we can say then is that if the epsilon neighborhood of P is in F complement, then it should be clear that the epsilon neighborhood of P intersect F, not F complement, must be empty, right? Right, so if this epsilon neighborhood is inside of F complement is just basically not F, then it follows that the intersection of the epsilon neighborhood and F would be empty, right? So therefore, we would say no point of F complement is a limit point of F. So no point of F complement is a limit point of F, right? Which implies, what does that imply? All of the limit points of F all of the limit points of f are in f, right? You got two sets, f and f complement. If no point of f complement is a limit point of f, then all of the limit points of f must be in f. Right? So that's the one direction. Right? So if f is closed, then all of the limit points of f are in f. Let's go the other way. Let's go the other direction. Let's assume now that f contains all of its limit points. So assume that f contains all of its limit points. Right? Now we wish to show that this is going to have to imply that f complement is open, which would mean that f is closed. Well, I'll just put that, i.e. f is closed. It's good to make sure you don't worry about writing too much when you're writing these proofs. They're for you. You just want to make sure you understand them, right? But if if we want to show that f is closed, we need to really show that f complement's open. So let's let p be in f complement, right? So if p is in f complement, then since f contains all its limit points, p cannot be a limit point of f because p is not in f. If p is in f complement, then p cannot be a limit point of f, right? We're assuming that f contains all of its limit points. P is not in f, so p cannot be a limit point of f, right? So therefore, the implication is then there exists an epsilon greater than 0 such that the epsilon neighborhood of p intersect f is empty. Okay. And what does that mean? Well, that implies then for that chosen epsilon, the epsilon neighborhood of p must be in the complement of f. Okay. Right? If the epsilon neighborhood intersect f is empty, then that means, this epsilon neighborhood is entirely outside of f, which means it's in this complement of f, right? So therefore, p would be an interior point of f complement. Okay, and then, that's pretty much it. P was arbitrarily chosen from f complement, so f complement is open, implies that f is closed. And so that's the end of the proof. It's bidirectional, so make sure you follow that one. That one I think is nice. It's a nice way to characterize closed sets. So closed sets are sets that contain all of their limit points. So if a set is open, there must be some limit point outside of the set. Certainly clear when it comes to intervals, right? If this is a, b, open interval, we know that a and b are both limit points, but a and b are not in a comma b, right? That's kind of a simple one to remember to keep this theorem front of mind. An open interval has clearly two limit points that are outside of it, right? So very good. Okay, all right, that's a good one. We're going to kind of use this idea of limit points and sets that do and do not contain all their limit points to define a new kind of set that I'm sure you have not heard of. I would bet money if you're taking analysis for the first time you've never heard of this kind of set. So let's say if E is a subset of the real numbers, let's let E prime denote the set of limit points of E, right? Then the closure of E, is defined as, there's different ways to notate this. Sometimes people just do E bar, sometimes they do E with a square around it. I'm going to go with that one. This is more fun to write. E closure, the closure of E, is equal to E itself together with its set of limit points. Okay, so E is the subset itself. Now there may be some set of limit points that are outside of E, and we can build E prime on E and that set of limit points. And so E together with its limit points, it defines the closure of E. Let's do a simple example here, just so we can conceptualize this a little bit. Let's let E equal the interval 0, 1, which is a subset of R. E is open, and every point in E is a limit point. Right, so hopefully that's clear. I mean, any point inside that open interval, I can draw an epsilon neighborhood around and still be inside of E. So every point in 0, 1 is a limit point. I can obviously do these kinds of things, right? Are there any other limit points, though? Well, yes. There's 2 of them, right? 0 and 1 are both limit points of E that are not in E, right? That's why E is not a closed set, right? It has 2 limit points that are sort of outside of it. Okay, and so what I can do then is I can create the closure of E, right? So E closure we know is equal to E or E prime, where E is the set itself and E prime is the set of all the limit points of the set. And so this would be, in this case, equal to 0, 1, the set E, combined with, union with this set, 0, 1, the closed interval. Right, now this one is almost exactly the same as this one. There's just 2 additional points here, 0 and 1, the endpoints. Right? And so the closure of E is just the closed interval, 0 to 1. So in the case of intervals, this is all that's happening. Right? When you have an open interval, if you want to close it, you just toss in the endpoints. Now, with sets that are not simple intervals, it's not always so simple. Right? But in the case of intervals, this is the way to think about it. All right, very good, very good. We've got a nice theorem to go with this closure idea. We'll use this throughout. Well, we'll use it somewhat. We'll certainly use it throughout the topology section, but we'll use it more even as we keep going. It's a little bit of a different kind of idea, though. One you've probably not seen. So if E is in the real number, E is some subset of real numbers, then there's 3 things we can say. First of all, the closure of E is closed, and that should be obvious, right? Almost by definition, right? E union its limit point, the set of all of its limit points, obviously is going to contain all of its limit points and would therefore be closed. That one is obvious. The next one is that E is equal to its own closure if and only if the set E is closed to begin with. That one obvious. That one also, I think, is fairly obvious. Okay. I mean, these are intuitively obvious. How you would rigorously prove them may not be obvious, right? But on the surface, these connect with concepts we've seen throughout this lecture that make it seem like these aren't hard to believe, right? And then the third one says that the closure of E is contained in F for every closed subset of F of R where E is contained in F. Right, so the closure of E, so if F is any closed subset of real numbers which house E, then the closure of F, or sorry, the closure of E would have to be inside of F, right? So E is a subset inside of F, and F is closed, then the closure of E must be in F, right? So if you close any subset that contains E, then the closure of E would have to be in that set. Okay, so we're not going to prove all of these. The third one is the one that's kind of the trickiest to understand, but it isn't hard to prove. That one's not hard to prove. One actually turns out to be, like, in my opinion, the trickiest one to prove. So let's look at that one. So proof, and this will be of 1. So we wish to show that the closure of E is closed. And how do we show that the closure, how do we show that a subset is closed? Well, we show that its complement is open, i.e. we wish to show that E closure complement is open. Okay. So we'll start by assuming something. Basically, we need to show that every point inside of this set here is an interior point. So let's let P be some point inside the complement of the closure of E, right? If that's the case, then P is not inside of the closure of E. Okay. And so that means that, and P not being inside the closure of E means that P is not in E, and it also means that P is not a limit point of E. Because remember, E, the closure of E is it kind of be thought of as two sets. It's both E and all of E's limit points, right? And so if P is not in there, it can't be in E, and it also can't be in this other set we called E prime. Okay, so that basically means that P is not in E, and P is not in E prime. Okay, and so that means there exists some epsilon greater than 0 such that the epsilon neighborhood of P, when I try to intersect that with E, it's empty. Okay. Okay, so we've got that the epsilon neighborhood of P is entirely removed from E, so that means the epsilon neighborhood of P must be in E complement. Now we would be done, but we actually have this E prime set to worry about too. So we also need to show that the epsilon neighborhood of P intersect E prime is empty. We need to show that one too. If we get both, so we've got this one, right? So we've got this one. If we get this one also, then what we'll have is that the epsilon neighborhood of P it's not in E, and it's also not in E prime, so that would mean that it must be contained in E complement and E prime complement, and that would be equal to E or E prime complement, which that is the set we're looking for. We want to show that the epsilon neighborhood is in there. Right, so we've got this one. This is the one we've gotten up to. Now this one we have to show next. All right, so how do we show that? So to see that the epsilon neighborhood of P intersect E prime is empty, what do? Well, what we're going to do is we're going to assume the reverse and derive a contradiction. We'll use the method of contradiction. So let's assume falsely that the epsilon neighborhood of P intersect E prime is not empty. Okay, so let's assume the reverse of this, right? We've derived this and shown this to be the case, but let's assume the reverse of it. Right, let's assume it's not empty. Actually, we haven't derived this yet. We're going to assume the reverse and see what happens, right? So if this is non-empty, then there's going to be some q in there. We'll say let's go ahead and let q be in epsilon neighborhood of p intersect e prime. And we can choose delta greater than 0 such that, I mean, this is always possible to do. We'll choose delta such that the delta neighborhood of q is contained inside of this epsilon neighborhood. Right? That's a simple thing, right? Q is assumed to be in this intersection. I can always choose some tiny little delta. This is just an interval. I can always choose some tiny little delta that's in there. Okay. So since Q is in E prime, right, by assumption, Q is a limit point of E. So Q is a limit point of E, and therefore, this delta neighborhood of Q and E is non-empty. Okay. But this is a contradiction. Where's the contradiction? Well, if this is non-empty and this is inside of epsilon neighborhood of P, then something else is non-empty that we've already shown to be empty. So we see that delta neighborhood of Q is a subset, right, by construction of the epsilon neighborhood of P. Right? If this is true, then if the delta neighborhood of Q intersect E is non-empty, then those two together imply that the epsilon neighborhood of P intersect E is non-empty. Right? But that's a contradiction. That's a problem. Right? So our assumption that the epsilon neighborhood of P and E prime is non-empty is in error. And so instead, what we can say is that we have this now. The epsilon neighborhood of P and E is empty, and the epsilon neighborhood of P and E prime is also empty. So those two things are empty. They imply, what do they imply? Well, you got E and E prime here, so they imply that the epsilon neighborhood of P and the closure of E is empty. And then the implication there is that this epsilon neighborhood of P, it's not in the closure of E, which means it's in the complement of the closure of E. Okay, and so P is arbitrarily chosen. P was arbitrary. And so the implication is that P is an interior point and basically all of the elements of E closure are interior. And so E complement is open and E is closed. There we go. All right, so we've got it. All right, so kind of a, I mean, it's obvious based on, I mean, well, not obvious, but it's clear, like it's not hard to believe that this is true, but it's a little bit tricky to prove, right? To really prove it, using the definitions and kind of falling back on it. Okay, so that's good. A couple more things that we want to touch on. So using this idea of the closure of a set, we can kind of recast the idea of the denseness of a set, right? So denseness we talked about was, this idea that this, for example, the rationals are dense in R means that for any rational number, I can't isolate it. I can't draw. I can't create a ball around any rational number that's small enough to not include more rational numbers, right? And so the idea of denseness, as is that a set D is dense in the real numbers if the closure of that set would require the entirety of the real numbers. In order to close the real numbers, in order to close this set D, I need all the real numbers. Right? The limit points are everywhere and throughout the real numbers. There's no way to close the set D in R without pulling in all real numbers. Right? So you can think about this in the context of the rational numbers. Q is dense in R means that the closure of Q, right, i.e. Q, and so Q and all of its limit points, right? Irrationals can be limit points of rationals, right? Basically, this is all of R. Okay. All right. So to get all of the limit points of the rationals, we need to pull in all of the real numbers. Okay. Q prime turns out to be R. So Q or Q prime is the real numbers. Okay. All right. Very good. So this is a very, very powerful stuff. And when we get into the next section, we'll talk about compact sets. But before we go, I do have one more concept that I want to break out here, and it's a little tricky, but it might come up later in the class. I just want to make sure that we cover it a little bit, right? And this is the idea of relative openness or closedness. So we'll write this as a definition. We're going to let X be a subset of R. Okay, and there's two parts to it. A subset U that's inside of X, a subset U of X, is open in X if for all P in U there exists an epsilon greater than 0 such that the epsilon neighborhood of P intersect X is a subset of U. Okay, don't freak out. We'll do an example in a second on this. All right, so a subset U of X is open in X, right? This is new terminology, open in. We've up to this point just said that a subset is open or it's closed, but now we're saying it can be open in a subset even if it's closed in general, right? Or some version of that kind of relativity, right? So there's the openness here, and then we'll also do the closed thing. A subset C in X is closed in X if X minus C is open in X, right? So it's just the reverse, right? So it follows the same pattern. A subset is closed if its complement is open, and that's what this is describing. This is the relative complement of C. Okay. All right, let's do an example, because this is not a totally obvious concept. So this is the best example I could come up with. Well, this is an example from the book I was looking at, but let's talk it through. So if X is equal to this interval, 0 to infinity, and U is equal to 0, 1, then U is not open in R, but is open in X. And then, like, why is this? Okay, so why would this be the case? Well, you just have to really kind of be careful about swapping in all of the sets here. Let's kind of go back to the definition. A subset, the definition says U of X, and in this case U would be 0, 1, and X would be R. So this would be your U, this would be your X. A subset 0, 1 of R is open in R, i.e. x, if for all p in 0, 1, i.e. u, there exists an epsilon greater than 0 such that the epsilon neighborhood of p intersect R, which was x in the definition, is contained in, so this set here is contained in 0, 1, the U set. So what does this mean? Right, let's draw a picture here. Here's a nice picture. So I've got my 0 down here, and I've got 1 up here. So when we're talking about the this interval 0 to 1, right, this is closed down here, and then it's open up here. Okay. Now, in the case of 0, 1, and in the case of u in R, or 0, 1 open in R, is it open in R? It's not open in R. And the reason is I can come up with an epsilon, right? I can come up with an epsilon, namely down here. This would be 0 plus epsilon, and this would be 0 minus epsilon. I can come up with an epsilon region of this point 0 such that a part of the region falls outside of U. Right? With this, in order for it to be open in the real numbers, there can't be an epsilon region that's outside of U. Right? So for all p in U, there exists epsilon greater than 0 such that that region is inside. Right? But here it's not possible. It's an endpoint. Right? So this part here, this part is not in 0, 1. Okay. Right? This is the intersection of the epsilon neighborhood and R. Now let's swap in the other piece, right? Let's say, so U is not open in R, but U is open in X. Right? So let's see what changes when I consider X instead of R. So a subset 0, 1 of 0 to infinity, this is your U and this is your X, is open in 0 to infinity, right? And it says it's open if for all p in 0 to 1, there exists epsilon greater than 0 such that what? Well, the epsilon neighborhood of p intersect 0 to infinity is contained in 0 to 1. Well, that's definitely true, right? Right? That's definitely true because the intersection of the epsilon neighborhood in 0 to infinity is what? Let's draw the picture here again so we can contrast them. Here's your 0. Right? Now, when I draw the epsilon neighborhood here, previously the intersection with R would have been this part. But now the epsilon neighborhood is just being intersected with 0 to infinity. So this is the only part that is in this intersection, and it is contained in 0, 1. Right? So it is contained. Up here, we had this part that was problematic. Here, the intersection, right? When you intersect with R, you get this extra part. When you intersect with 0 to infinity, you don't get that part. You just have this piece. And so that is contained in 0, 1. Okay, so kind of a tricky idea. I mean, down here you basically have that the epsilon neighborhood of P intersect 0 to infinity. The problematic part is this closed endpoint here. And the intersection there is just 0 to 0 plus epsilon. And that is certainly inside of 0 to 1. Okay, so that's kind of the tricky part that makes this example kind of difficult to understand, or and also interesting. Okay, we'll leave it at that, and when we come back next time, we'll continue on with this structure of point sets, and we'll delve into the very interesting idea of compact sets. Until then, take care.